Alrighty, so we have a warm-up right here. Find the derivatives and pause video because I'm about to do these problems myself. So I took the derivative using the power rule. So I looked at all of these exponents and then used those to find out what the derivative would be. And I talked about it in a previous video. Now for the next one, you have to be a little tricky because this particular guy, we don't really know what it means unless you know what a fifth root means. That's really x to the 1/5. So using this, try to take the derivative. So it should look something like this, but I'm not happy with the way this guy looks. So let's erase it. Instead of saying x to the -1/2, I'm just gonna go and put square root of x on the denominator. And then instead of having x to the -4/5, I put that in the denominator. I'm gonna have to remember what that said. Fifth root, that's a 5 of x to the 4. There we go. And that's the way I would probably write it. What is the instantaneous rate of change at x equals 3? So first take the derivative. The instantaneous rate of change will be -13. And is the function increasing or decreasing? Decreasing, since the derivative is negative. For the last problem, you're going to be plugging in pi because we're just trying to find out the limit, and unless the function becomes undefined, you can just plug them in. For cosines and sines, I can plug in whatever I want. So the cosine of pi is -1, so -2 times -1 gives me, -2 times -1 gives me +2. Let's move on. Alrighty, so let's do this problem. Pace Walker enters an 8th walkathon. She starts off at 4 miles per hour, speeds up as she warms up, then slows down as she gets tired. She estimates that her speed is given by this equation right here, where t is the number of hours since she started and v is in miles per hour. Pace walks for 3 hours. Plot the graph of Vt as a function of t for these 3 hours. Sketch the results on your paper. Be sure to use a calculator in radian mode. So we are doing this on the graphing calculator. I went through the trouble, and yes, my thumb has an extraordinary amount of hair on it, of graphing it. I went through the trouble to go to the library to get it. Hard to see when I'm typing with that iPad in front of me. So plus, and then sine, what is that sine? Boom. And then 1.4 times x. Alright, so we're gonna do this, but I'm gonna show you a nice little thing. So as expected, it's a sine function with a where it's shifted up, and fantastic. That's gonna be in the video. But we're going to change some stuff up. For instance, time cannot be negative. Also, we only care about the time to go all the way up to 4. Was it 4? No, 3. Because it's 3 hours. We're not going to have a negative y. And our amplitude is going to be like between, because it's 4 plus, sine alternates from -1 to 1. We can probably start at 2, really 3, but I don't want to push the limits, and 6. So I do understand it's going to be between 3 and 5 because it's like 4 minus 1 and 4 plus 1, but I don't want it that way. There we go. And here we have it. That's what the graph is supposed to look like. Look at this bad boy. Alrighty, hopefully that helped. How far did Pace walk in 3 hours? So when you find a distance for a velocity graph, then that means we're going to have to find the area underneath the graph. Now they tell us that we're using the trapezoidal rule and we're supposed to use 6 trapezoid. So let's find out the width of every trapezoid. So the width of every trapezoid is going to be 0.5, and now we can use the trapezoidal rule. I can't apologize enough for my handwriting, but since I'm talking about it, we should be fine. So it's 1/2 because the trapezoid area has a half in it. And then this is really the height of the trapezoid, but as far as we look at the x-axis, it's like the width of, it's like the delta x, which you will learn later. We have the first term, which is f of 0. We have the last term, which is f of 4. And then all the terms in between happen twice because when you put all of the areas next to each other, you will see two f of 0.5s. You will see two f of 1s, two f of 1.5s. So these things happen 2 times, which is why they're inside of they're inside of a parenthesis that has a 2 up front. So I hope that makes sense. So 2 times these values because these really happen 2 times. Let's move on. So I use the calculator to find out what my values are, and they're right here. You notice that I'm actually doing 4 decimals. That's because I'm trying to change my ways. I think we're going to do it where we round to the 3rd decimal every single time. And just as a caution, I'm going to make sure that all my numbers have at least 4 decimals. Let's plug into the equation. I just noticed I made a mistake, and the mistake is right here, and I fixed it. So, plug in, see what you get. So after multiplying 1/2 times 0.5, I ended up with, let me get the highlighter ready, 0.25, and then the first and the last term, which is right here, and 2 times all of the inside ones. So 2 times this, this, and this, and the last one, of course. So when you do this, I ended up with 13.021. If you remember, we were looking for how far we went, so the answer is 13.021 miles. And the reason why I said miles is because we were dealing with a problem that was talking about miles. What I mean by that is, if you read the question, I was talking about, let me get to use the highlighter. I was talking about walking at 4 miles per hour, and we plugged in hours. So the distance, the distance unit that we should be using is miles. Okay. To talk about it in a little bit more detail, we talked about the area underneath a velocity versus time graph. So the area underneath here represents the distance. So how do we know what kind of distance we have? Meters, miles, feet? It really depends on how the velocity is set up. And by the way, it's set up right here again. When the velocity is in meters per second, then the time is seconds, and the distance that the area represents is meters. In this case, it's miles per hour. So when you use time being hours, then your distance is going to represent miles. So you have to really look at these units to figure out what the proper answer would be. For the last part, how fast was Pace walking at 3? Well, that's simple. You simply just plug in 3 and get your answer. Try to get 3 decimals. And then, by the way, we saw this number earlier. When did her maximum speed occur? What was her maximum speed? Okay, we are looking for when the velocity equals 0. As a matter of fact, we're kind of looking at when this line happens, when this tangent line occurs, when we have a horizontal line. So what is this point that we're talking about? Okay, so go ahead and pause the video and try to figure it out. When is this derivative equal to 0? So when we go back to a graphing calculator, we want to use the calc option. So press second, and then for the trace above, you see calc. You press calc, and then it allows you to do a bunch of things. We want to know what the maximum is. So you press maximum, and then it's asking, do you see how it says the left bound? Well, the left bound's about right there. So I expect my value to be here somewhere, but I'm going to use the left bound, boom. And then once the right bound, which should be about right here. The reason why it does it is because there's a difference between absolute maximums and local maximums, and maybe we're looking for a local maximum. So guess. Is that what's telling me? Or is it asking me if I want to guess? Yeah, it was asking me if I want to guess. Alrighty, the maximum is 5, and it happens at 1.121 996 hours. We're gonna round it to 1.120 because the 9 rounds up as well. Rounds the 1 up to 0. No, that's incorrect. We're gonna round it to 1.122 hours. That's it. That's how you do it. So, an electric car problem. You have been hired by an automobile manufacturer to analyze the predicted motion of a new sports car they are building. When accelerated hard from a standing start, the velocity of the car is feet per second. So our distance would be feet, like I talked about in the previous video, and our time needs to be in seconds. And here's the equation. So let's do this problem. So you want to draw the graph with this domain. So let's go back to our graphing calculator. Alrighty, so we have our graphing calculator. I plugged in the equation. We're going to now worry about that domain they gave us. The domain, you go get to the window. I already set it up. You see how I set from 0 to 10? That's a domain. Also, I know that it's going to be very low at 0 because when you plug in 0 for x, you're going to end up getting a 0 inside the parentheses, so 0. And then it's going to level off at 100 because as x gets larger, that 0.9 is going to get really, really small. And let's see what's going to happen. Alrighty, so we got a little graph. I noticed that I can probably make it look a little nicer if I don't go. By the way, if I was going to like 100, then you will see that it actually does level off at y equals 100. But that's not what we want. We're gonna want, yep, that's gonna be in the video. My wife just texted me. Delete. Alrighty. So we had this graph right here. I want to make it look nice. I'm probably gonna say to stop at 70. So let's put 70. By the way, you don't have to do that. If you had the first time around, you're absolutely fine. Alrighty, so we got that. We got it figured out. Next part is, what is the range of the velocity function? That's easy. You just have to find out. We notice in a function that it has a minimum right here and maximizes right there. So all you have to do is find out what happens when t is 0 and what happens when t is 10. So the range is going to be from 0 to 65.132. By the way, these are feet per second. And I forgot to put that right there. So approximately how many seconds will it take for that? So when is y equals 60 feet per second? So let's find that out. So you plug in 60, then you put the equation. You solve for the equation until you get to this place right here, and you can either natural log or log both sides, or you can use a funnel function inside your graphing calculator. So you're right here. Let's go with math. We want to do some math. And you go all the way down to where it says log base. And if you remember, it said 0.4 and then 0.9 to the t. So 0.9 to what power equals 0.4? Log base 0.9. And then that's supposed to equal to 4. No, sorry, 0.4. Unless I misread it. Okay, so that. Alrighty, so that would be the answer. Well, we can test it if you don't trust what I just said. So 0.9 raised to the 8.697. Boom. Yeah, that's pretty close to 0.4, right? So here the next place saying approximately how far will the car have traveled when it reaches 60 feet per second? So we're looking for the area again, and what I noticed here is that they straight up did the integral. The calculator does figure out the integral for you, so let's do that. So again, we're going to go to our math button. And when you go all the way down, you will see where it has like finding the derivative and the integral. So over here, you simply have to plug in the numbers and it will give you the answer. Just make sure that if you put like an x right here, then this should be an x as well. That being said, that's how you do it. I also should talk about a little bit more. When I talk about plugging it in, that's kind of what it's supposed to look like. And just so you know, for an integral, this part right here represents the beginning domain, where this right here is the end. So starting point, final point. And then this is where the function, this is where you plug in the function. So you plug that stuff in, you press enter, and it does give you the answer. All right? So I hope that helps. For the next one, it says, at approximately what rate is the velocity changing when t equals 5? Go ahead and just use the method where you have t equals 5 and then 5.001. And lastly, what's the last thing that needs to be done? I just want to make sure I get everything out of the way. It says, what special name is given to the rate of change of velocity? Well, that would be the acceleration. So they're asking for the acceleration at 5. And since we haven't really talked about shortcuts for derivatives, let's go ahead and do the method I just told you to use. So when we actually use the method we just talked about, we find the 5, we find the 5.001, plug it in this bad boy, we get our answer, but we have a graphing calculator. Why should we bother with calculations if we can do the derivative? Alright, so we have a derivative, we're going to do the derivative of x, and then of this, can I just copy down this function? Can I dare? Yes, I can. Yes, I can. Alright, so that's x as well. Graphing calculus are pretty awesome, but you know, how much cheating is going to happen with graphing calculator? Let's see what they get. So they got 6.221. Yeah, not too shabby, pretty close. So the answer is 6.221. And it's acceleration, so it's going to be, I believe it was feet per second, I kind of forgot. So it would be feet per second squared, whatever the units were. Alrighty, that's it.